Have you ever really thought about what holds our modern world together? I mean, what's the actual backbone? You might think steel, or maybe silicone, but it's actually something way more fundamental. Invisible beams of light and tiny, tiny threads of glass.
It sounds like something straight out of science fiction, right? But it's not. It's the reality we're all living in every single day. So in this explainer, we're going to tackle that exact question by looking at two technologies that, when they came together, literally changed everything.
All right, let's dive right in. If you want to understand how we send information using light, you first have to understand the light source itself, and that, of course, is the laser. So the name LASR, it's not just some cool-sounding word. It's actually an acronym, and it spells out the exact recipe for how it works. Now, the two most important words to remember here are stimulated emission. They are the absolute key to this whole thing, and we'll see why in just a minute. To really get why laser light is so special, just picture the light from a normal light bulb. It's like a big, chaotic crowd, with everyone yelling different things in every direction. That's what we call incoherent light. A laser, though? A laser is totally different. It's like a perfectly trained choir, where every single voice is singing the exact same note at the exact same time in perfect harmony. That's coherent light. It's organized, it's pure, and it is incredibly powerful. And because it's so organized, laser light has some pretty amazing superpowers. It's highly directional. That's why a tiny laser pointer can make a dot on a wall way across the room, instead of spreading out like a flashlight. We already know it's highly coherent. All its waves are in perfect lockstep. It's also monochromatic, which just means it's one single pure color. And you can focus it down to a point so sharp that it concentrates an immense amount of energy, making it unbelievably bright.
So, that's what a laser is. But how in the world do you actually create this perfectly organized beam of light? Well, to figure that out, we have to shrink ourselves way, way down, right to the atomic level.
It really all boils down to three ways light and matter can interact. First, an atom can just soak up a photon, which kicks it into a higher energy or excited state. That's absorption. Second, that excited atom can just randomly decide to spit out a photon and drop back down. That's spontaneous emission. It's what's happening in a light bulb, and it's totally chaotic. But then there's the magic trick, stimulated emission. This is where a photon comes along and hits an atom that's already excited. When it does, it doesn't get absorbed. Instead, it triggers that atom to release a second photon that is a perfect, identical clone of the first one. Same frequency, same direction, same phase. Suddenly, one photon has become two.
Now, to get that incredible chain reaction going, you need a situation that's, well, completely unnatural. Normally, most atoms are just chilling out in their calm, low-energy ground state. To make a laser, we have to create a condition where there are more atoms in that high-energy excited state than in the calm one. It's this completely upside-down arrangement, and it's called a population inversion.
Okay, so how do we make that population inversion happen and kick off the chain reaction? It comes down to three key parts. First, you need an active medium. That's the stuff that will actually produce the light, like a ruby crystal. Second, you need a pumping source, something like a super powerful flash tube, to blast the medium with energy and create that population inversion. And finally, you need an optical resonator, which is basically two mirrors. They bounce the photons back and forth through the medium, creating a massive cascade of stimulated emissions until the light gets so intense it bursts out one end as a powerful, perfect laser beam.
Okay, we've done it. We've created the perfect beam of light for carrying information. But, a beam of light is pretty useless if you can't tell it where to go. How do you get it across an entire ocean? For that, you need the ultimate light pipe. And here it is, the fiber optic cable. Its design is just pure genius because it's so simple. It's got three layers. Right in the middle is the core, the strand of unbelievably pure glass that actually carries the light. Wrapped around that is the cladding, another layer of glass that acts like a perfect, flawless mirror. And on the very outside is just a tough coating to protect the whole thing.
The physics that makes it all work is a beautiful principle called total internal reflection. See, when light zipping through the core hits the wall of the cladding at a really shallow angle, it doesn't leak out. It can't. Instead, it reflects perfectly, bouncing its way down the fiber, zigzagging for miles and miles with almost zero loss of signal. And the one simple secret rule that makes this whole magic trick possible? The glass in the core has to have a slightly higher refractive index than the glass in the cladding. A refractive index is just a measure of how much a material bends light.
That tiny difference is what forces the light to reflect back on itself, trapping it perfectly inside that core.
So let's put it together. We've got the perfect, controllable light source, and we've got the perfect, almost lossless light pipe. Now we can see how this incredible partnership kicked off the communication revolution that we're all living in right now.
I mean, it really is a match made in heaven. The laser gives us this pure, intense beam that we can flash on and off billions of times a second to represent all the ones and zeros of our data. And the fiber optic cable? It gives that light a super efficient, protected highway to travel on, guiding it across countries and under entire oceans.
And the amount of data they can carry is just staggering. Think about this. A pair of old copper telephone wires could barely handle a dozen phone calls. A single optical fiber, again, thinner than one of your hairs, can carry tens of thousands of conversations, all at the same time. It was a massive leap in bandwidth, the kind of leap that made things like streaming 4K movies and the entire smart home possible.
And that's exactly why fiber optics took over modern communication. They just solved all the old problems we had with copper wire. You get massive bandwidth for way more data. The signal can travel for miles without needing a boost, and because it's light, not electricity, it's totally immune to interference from things like power lines or even lightning.
But here's the thing. Connecting the world was really just the beginning for this dynamic duo. Mastering light has unlocked unbelievable applications in pretty much every field you can imagine.
Take medicine. Lasers are used as scalpels that can cut tissue and seal blood vessels at the same time, which means almost no bleeding during surgery. They reshape your cornea in LASIK eye surgery, they can remove tattoos, and when you pair them with a fiber optic cable and an endoscope, doctors can see and operate deep inside the human body without major incisions.
And in industry? Oh, they're everywhere. High-powered lasers cut and weld steel with microscopic precision. They're the heart of 3D printers that can build complex metal parts out of powder. They engrave serial numbers on everything from microchips to car engines. And yep, every time you hear that beep at the checkout counter, you're seeing a laser barcode scanner do its thing.
This tech has also pushed the absolute boundaries of what we can do in science and defense. Lasers guide bombs and missiles with pinpoint accuracy. They've measured the distance from here to the moon, down to the centimeter. And in one of the greatest scientific discoveries ever, they are the key component in the massive detectors that finally proved Einstein right and found gravitational waves.
And the fibers themselves, they're not just dumb pipes for data. The military uses them for communication lines that are impossible to tap into. They help guide missiles with incredible accuracy. They can even be turned into long-distance sensors, detecting tiny changes in temperature all along a pipeline that's miles and miles long.
You know, when you step back and look at the big picture, the conclusion is pretty obvious. These technologies are the invisible architecture of the world we live in. From the internet that connects every one of us to the tools that heal our bodies, we have completely reshaped our world simply by learning how to master light.
We've seen light carry all our data, perform surgery with incredible precision, and cut through solid steel. It just makes you wonder, what amazing problems are we going to solve with it next?